So it's time to sit down. This is impressively punctual. 2:00. But some people should still sit down and start becoming quiet. Okay, so the first talk of this session is a review talk by Monica Guica on TT-bar deformations and holography, review and open questions.
Okay, so I'd like to start by thanking the organizers for the invitation to speak. So as Finn mentions, I'll do a review on TT-bar deformations and their holographic interpretation. So first of all, what is the TT-bar deformation? Well, TT-bar is, I can hear myself actually. It's an irrelevant deformation of two-dimensional QFTs that results in a UV-complete QFT that's, however, intrinsically non-local in the UV. So you take your QFT, you do this deformation. For generic irrelevant deformations, so those are not very well defined because of a proliferation of counter terms. That's one thing. And the second thing is that if you take the theory produced by a generic irrelevant deformation and go to high energies, more often than not, it doesn't make sense. It has a cutoff. What's very special about the TT-bar deformation is that, first of all, there's a precise way to specify the deformation is all along the flow. So you can define it at a finite deformation parameter, I'll call it mu. And moreover, this flow preserves the integrability if initially present. And secondly, if one takes a theory, one of the deformed theories, and goes to the UV, its S matrix appears perfectly well defined, so indicating the theory is UV complete. However, the UV behavior is not captured by a UV CFT fixed point, so this is out of the standard setup. I should also mention that TT-bar flow is not an RG flow. You're not integrating in or out any degrees of freedom. You have as many degrees of freedom here as you have here. Okay, so why is this deformation interesting? It's interesting for very many different reasons, and actually there have been people from very different communities working on it. So let me just try to make a few points. So first of all, you may be interested in it for purely theoretical reasons, into, what is the possible space of QFTs, or more narrowly, you can try to classify integrable two-dimensional QFTs. So here, a more precise question is the following. So if you start with some integrable S matrix in 2D, so you can just consider 2 to 2, which satisfies all the bootstrap axioms, it turns out that you can find an equally good solution to the bootstrap axioms if you multiply this guy by a so-called CDD factor, where these alpha S are just arbitrary coefficients. So then the question is, do the theories with this S matrix, do they correspond to some meaningful QFTs, and what are their properties? TT-bar turns out to be the answer for S equal to 1. And not only that, so then you can ask, are the TT-bar properties sort of generic in among these theories? And more recent work suggests that some of its properties actually may be generic. So it's really interesting to study it in this context. A second reason to study TT-bar is through its relation to the QCD string. So it's a fact of life that TT-bar deformed free bosons give you the Nambu-Goto action, which is the lowest term in the effective action for a string, for example, the QCD string. Of course, TT-bar is integrable, so you need to break that integrability to get sort of realistic results, but it's still the case that TT-bar is a good starting point for that expansion, giving good agreement with lattice simulations. Yet another reason to be interested in TT-bar is due to non-ADS holography. So there, the idea is that any such sort of irrelevant, finely tuned flow, starting from a CFT and going, giving you a UV complete theory, may help you understand some instances of non-ADS holography. So you see here the IR CFT translates into some ADS spacetime in holographic terms, and then the irrelevant deformation translates into some non-normalizable deformation of this ADS. But then the fact that this theory is UV complete without having to add in any new degrees of freedom suggests that this throat that you're building over here doesn't go into full asymptotical flat string theory, but there's some additional decoupling limit, and which has some non-ADS geometry, which is described by this non-CFT. So that's another reason it's interesting. And there's some other holographic reasons very different for being interesting, which I'll explain. And last but not least, one reason that so many people are interested in this deformation is that it's highly tractable. There are a lot of things that you can solve for exactly. So even though at the end of the day you're interested in deformations of TT bar in all these different directions, this is a very good, starting theory to be studying and really understand in detail. Okay. So the plan of my talk is to start with a review of the basic field theoretical properties of TT bar, and then I'll discuss the holographic dictionary for itself, and also for an analog of the TT bar deformation that is actually relevant to non-ADS holography. And I should say that the literature on TT bar is huge, and there are many variants and many interesting directions. I will definitely not have time to go into most of that, so I apologize to the people. So I'll just concentrate on TT bar and mention maybe a bit about other deformations, but only when it's particularly interesting. Okay, so TT bar is a particular instance of the so-called Smirnov-Zamolodchikov deformations, which are basically irrelevant deformations of two-dimensional QFTs, which are constructed as bilinears of two higher spin conserved current, J and JB. So the deformation proceeds in two steps. One first defines this Smirnov-Zamolodchikov operator, and one does that by taking this particular antisymmetric combination of the two current components at two nearby points. And then Smirnov-Zamolodchikov showed that in the coincidence limit, you get one operator with a constant coefficient, and then everything else is derivative terms. So this basically defines this operator up to total derivatives. Okay, that's the first step. The second step, you add this operator to the action and you deform it incrementally. So what does that mean? In the initial QFT, I add my TT bar or Smirnov-Zamolodchikov operator. Then in the deformed theory, I recompute the currents, which do change. I recompute the operator and I deform by that operator and so on. And you can do this for any two currents, but particularly interesting examples are TT bar, where you choose the two currents to correspond to components of the stress tensor, antisymmetrized to get Lorentz invariance. And if you want to see what it really looks like, it's in complex coordinates, it's basically T times T bar minus trace squared. So in CFT it's TT bar, but more generally it's like determinant of T. So this is a 2,2 irrelevant operator in two dimensions, so its coupling has dimensions of length squared. You can also do things where you take one U1 current and the other thing being T bar, so the generator of right moving translations. This is called JT bar. It breaks Lorentz invariance, but it has the nice property that when you act on it with a CFT, it preserves half of the conformal invariance of the CFT. So the resulting theory is local and conformal on the left, and all the non-locality is concentrated on the right movers. And that turns out to be a huge simplification with respect to TT bar, which is a fully non-local theory. You can also do arbitrary combinations of TT bar and with various U1 currents and so on, and they're well understood. Also, if your original theory is integrable, you can consider generalized TT bar constructed from the higher spin currents associated to integrability, and this corresponds to other CDD factors. So the point here is that this is a well-defined irrelevant deformation that produces a theory that's non-local at the scale of the deformation, but that has been argued to be UV complete. Okay, so let's now discuss some of the basic observables one has in this theory. And one of them is the finite size energy. So what you do, you take the TT bar deformed theory and you put it on a cylinder of radius r. And the point is that the Hilbert space of states is unchanged. It's only the Hamiltonian and its eigenvalues that change. And given that this is a continuous deformation, you can basically just use first order quantum mechanics theory, quantum perturbation theory to study the flow of the energies and the energy eigenstates. So this you should recognize, where d mu h is basically the integral of the TT bar operator. So now this d mu h can be written in a nice way, and it turns out that the only term of it that actually contributes to the flow of the energy eigenstate, it's a contribution that actually factorizes between the two stress tensor components, and that only involves the spatial integral of the stress tensor. So you can just write it in terms of energy, momentum, and some pressure term. And basically this lies at the heart of the solvability of the spectrum of the theory, because you basically get a universal Burger's equation for the flow of the energy eigenstates, which basically determines them in terms of the spectrum, finite size spectrum of the undeformed theory via an equation like this. Okay, so that's one important result. Now, if your theory happens to be an integrable QFT, you can actually relate the finite size spectrum to the deformation of the S matrix via the thermodynamic Bethe ansatz, and you basically get the CDD factor I discussed. And this sort of flow of ideas and the structure actually generalizes to all these universal deformations, so constructed just from currents and stress tensors. I should say that these two deformations are at the core of the many of exact results that have been obtained in this domain. And as was shown by these people, actually the S matrix deformation doesn't really rely on integrability. So this result, which I've now generalized to an arbitrary number of particles, holds for an arbitrary non-integrable QFT. Okay, so these are quantum results, but you can get a glimpse into the solvability also even better classically. For example, you have an exact expression for the deformed Hamiltonian density of this theory for an arbitrary undeformed Hamiltonian. So it's totally closed form, and this is for safety. Okay, good. So those were for general QFTs. Now, you can get a lot of mileage by assuming that the C theory is a CFT, so you know the initial energy spectrum. And then you can solve this equation and find this nice closed form formula where I reinstated the momenta. And you can also do thermodynamics by noting that the deformation doesn't really change the density of states, so you still have Cardian entropy at the original energy, which you now have to express in terms of the deformed energy, so you get something like this. And this formula has some notable features. So first of all, the R goes to 0 limit. The energy doesn't go like 1 over R, so this already tells you you can't have a CFT in the UV. But more precisely, for mu greater than 0, you notice that the ground state energy, which were here, it was given by the Casimir energy on the cylinder, becomes complex if the radius is smaller than this minimum radius. Relatedly, you notice that the entropy has Hagedorn behavior at high energies, and the Hagedorn temperature is the inverse Armin. For mu smaller than 0, so here you just have the ground state and maybe a bunch of couple other states whose energy becomes complex. For mu smaller than 0, it turns out that all states with energies greater than this quantity acquired imaginary energies, so you're only left with a finite number of real energy states. So here I come to an open question in this field. What is the interpretation of all these imaginary energies? Physically, what you'd really like to see is some sort of instability, but I don't think anybody has an idea about that. There have been proposals to just truncate away the imaginary energy states. Another thing you can do, you can try to interpret them somehow, which these people did. So basically what they noted is that these theories on finite energy backgrounds, they may exhibit superluminal propagation, which is fine when you're on an infinite line, but can lead to closed time-like curves if you're in compact space. And they noted that the imaginary energies kick in precisely when the time advance due to this equals the radius of the circle. So based on that, they proposed that the positive mu TT bar shouldn't be put on a cylinder of radius smaller than Armin. This is dual to, it doesn't make sense for temperature higher than Hagedorn. And for mu smaller than 0, the theory isn't supposed to make any sense on any compact size. Okay, so those were some general results. You can actually get a lot of intuition into the physics of TT bar so it turns out that there's a nice connection to the worksheet between TT bar and the worksheet of a string. So this is a fact of life. If you take d-2 TT bar deform free bosons, you just get the Nambu-Goto action for a string in d-dimensional target space in static gauge. So you align the string time and space to the target space directions. Which basically tells you that the TT bar deformation simply corresponds to a change of gauge in the Nambu-Goto action. You go from conformal gauge for the free bosons to the static gauge which describes TT bar. So from that perspective, it sounds like a really trivial deformation, except that, this is a large gauge transformation. It non-trivial affects observables. And it turns out that this picture for the free bosons actually generalizes to all possible TT bars. So generally it's true that the TT bar deformed theory and the undeformed one in these coordinates are related by a field-dependent coordinate transformation, which involves these integrals of the stress tensor. This observation has led to a general definition of TT bar deformed QFTs by coupling to topological 2D gravity. So basically, you take your original QFT, you put it on a curved background, and then you add this term with some auxiliary fields which basically force the background to be flat. And then you see that the field-bound equation of motion basically enforces this coordinate transformation. This was proposed by these people, and actually this action can be derived roughly by applying the Haber-Stratonovich trick to TT bar. Then you introduce some integral over random metrics, but then they're actually constrained by stress tensor conservation. What is nice about this formulation of TT bar is that, first of all, it's fully non-perturbative. So in the Smirnov-Zamolodchikov deformation, you still needed to be able to talk about the stress tensor. Here you don't. And it perfectly reproduces the flow of the energies and the deformation of the S matrix in full generality. I should also say that there was a previous formulation of this, roughly equivalent in terms of GT gravity with a cosmological constant. And there's also an interpretation of it in terms of 2D gauss-free massive gravity, where this is the mass squared of the graviton. Okay, so given this worldsheet interpretation or GT gravity interpretation, a question that comes to mind is, should this TT bar deformed QFT be thought of as a non-local QFT, as I introduced it, or should it be rather be thought of as a theory of 2D quantum gravity? And the issue is subtle because in 2 dimensions you don't have a propagating graviton, so you don't really know what gravity is. So in this very nice initial paper, they argued it's a theory of 2D quantum gravity, and that was based on the physical properties of this S matrix, which has very gravitational features. It introduces a time delay proportional to the energy, and also minimum length in scattering set by the coupling. However, you might say that TT bar is a non-local QFT if you can somehow make sense of off-shell observables sort of non-perturbatively. And in that direction, Cardy has done some very interesting analysis of correlation functions of quasi-local operators, where she showed that basically the main effect of the deformation is to attach a gravitational Wilson line to this operator. So they sort of become non-local, but it's sort of controllable, except that there are a lot of divergences. For the particular case of TT bar deformed CFTs, we have been able to show that these theories actually have some non-local generalization of Virasoro times Virasoro symmetry. And since this is a bulk symmetry, it suggests that the theory is really a QFT, and more precisely, it should be thought of as a non-local CFT. And sort of in this vein, an interesting question is whether these symmetries can actually fix the correlation functions of special operators. So you want to talk about sort of analogs of primary operators. So just to give a couple more detail. So the way that we find the symmetries is sort of abstract. We look at the flow of the energy eigenstates on the cylinder, and then we define some operators that flow the same way, and by construction satisfy a Virasoro algebra. And these generators actually turn out to be conserved by some special properties of Tt bar. So we find the symmetries, but this argument is super abstract. It's fully quantum mechanical, but it's super abstract. So you may ask, okay, what transformations do these generators implement? And in some work in progress with Ruben Monden and Yanis Siares, who is here, we showed that in a classical limit, the flow generators are the field-dependent radius of the field-dependent coordinate I talked about before, which is proportional to the energy, and times basically the Fourier mode of the left-moving Hamiltonian with respect to this field-dependent coordinate, which you have to be very, very careful how you define because it's simple. Okay, so what's the upshot? Well, the upshot is that whereas these guys, we can get them from this nice quantum mechanical flow, it's these guys that are the physical generators of the symmetries, whose the zero modes are translations. And okay, this is where our knowledge stops in Tt bar. But in the related Jt bar deformation, which is simpler, the analogous relationship between the flow generators and the physical generators allows us actually to define analogs of primary operators, basically their primary but the word identities with respect to the physical guys. And then we can show that their momentum space correlation functions are entirely fixed by those of the undeformed CFTs. They're actually no local correlation functions, but they're entirely fixed. So, of course, the hope is that something similar could be made for Tt bar, and that if that's the case, it would mean that we can find basically a one-to-one correspondence between all the observables in the undeformed theory and in the deformed one. So they're basically, Tt bar is just looking at the original CFT through these dynamical coordinates, roughly speaking. So the deformation is a bit boring, but in sort of an interesting way. Okay, very good. I still have a lot of time. Okay, so that was the field theory presentation. Now, let me now discuss the holographic dictionary for these theories. Okay, so I want to concentrate on Tt bar deformed CFTs, and I want my seed CFT to be a holographic one, large C, large gap, dual to Einstein gravity with a bunch of low-lying matter fields. And because the Tt bar deformation is double trace in ADS-CFT parlance, it basically corresponds to mixed boundary conditions for the dual bulk field, which in this case is the non-dynamical graviton. And we know very well how to deal with mixed boundary conditions in ADS-CFT. There are two steps. First, we use the Haber-Stratanovich trick to basically relate the deformed partition functions in presence of sources to the undeformed one in terms of as a function of the sources shifted by the waves of the operator. So this is a pure field theory steps, which is pure field theory. And then we use the undeformed holographic dictionary to translate this into bulk terms. Okay, so if you do this over here, so we start with 3D gravity. The asymptotically ADS3 metric, has a Pfaffman-Graham expansion like this. These two terms are universal. These depend on the matter fields. With Dirichlet boundary conditions, this corresponds to the boundary metric, and this guy corresponds to the expectation value of the trace subtracted stress tensor. So now we apply these two steps. So the first step tells us that the metric in the deformed theory is given by the undeformed metric, and then it's shifted in a nonlinear fashion by the wave. It also gives us the stress tensor wave, but I didn't write it. Okay, so this is the field theory step, and then the gravity step, we just translate this into gravity terms using the undeformed dictionary. So basically what we get is that the holographic dual to Tt bar deformed CFT is ADS3 gravity with this particular combination of the asymptotic metric coefficients fixed. And this works for both signs of the deformation and only depends on asymptotics, so you can turn on as many matter waves as you want. It works. Now, if I take this TT bar metric to be the flat metric, I can just build the gravitational phase space. So it's going to have fluctuating G0, fluctuating G2 with this combination fixed. And you can compute the deformed energy spectrum and find perfect match to the field theory formula. Okay, let me make some possibly trivial remarks. So, to my knowledge, this is the first instance of mixed boundary conditions on the ADS3 metric, where the bulk and boundary theories have independent definitions. So the standard situation that one is used to is that you're given some bulk theory with some boundary conditions, which you have to check that they're consistent and so on, and the charges are finite and so on, and then you infer from those the properties of the boundary theory. Here you actually have them independent, and so you can actually check the dictionary. Second remark is that this is a nice example where you see that the change of boundary conditions on ADS3 entails a radical modification of the boundary theory. It goes from local to non-local. And the third comment is that this gives us a good opportunity to do precision holography. So I showed you the perfect match of the bulk and boundary spectrum, but you can do symmetries. So the asymptotic symmetries of this space-time consist of two copies of Virasoro. This is how we initially thought about looking for Virasoro symmetries in TT bar, but actually the match turned out to be a lot more subtle. And if we understand correlation functions in TT bar, we can try to match them, entanglement entropy, and so on. So this could be a nice setup to test and sharpen the rules for asymptotic symmetries and holographic dictionary in this kind of setting. Okay, so I showed you how in the general case you get these mixed boundary conditions, and you could have matter fields turned on. Now let's concentrate on pure gravity. So in pure gravity, it turns out that the Pfefferman-Graham expansion of the metric truncates to this. So this is the full metric, and then this TT bar metric that I showed you over here turns out to precisely coincide with the induced metric on the surface of rho c is minus mu over this. So you see that for mu negative, you actually get a finite a surface at finite radial distance in the bulk. And not only that, but also the expectation value of the stress tensor coincides with the Brown-York stress tensor at rho c. And third coincidence is that, so I told you in our mixed phase space, the boundary metric fluctuates. In this case, there's actually a coordinate transformation that takes this surface in that fluctuating in that mixed phase space to the constant Schwarzschild radius surface in standard BTC. So with Brown and no boundary conditions. Okay, so you basically have these three coincidences. It's really magical coincidences that happen. And this can help explain one of the earliest observation that was done, in the first holographic correspondence that was proposed for TT bar by Megao, Mezei, and Verlinde, where they noted that the TT bar deformed energies at mu negative precisely coincide with the energies of a black hole in a box. So this basically implied that. Okay, so that was one of the nice observations in this paper. Another interesting observation was that, so in negative mu TT bar, so there's the infinite set of imaginary energy states. They noted that the onset of the imaginary energies precisely coincide to the moment where the Schwarzschild radius of the black hole you have in the middle reaches this sort of cutoff surface. So that basically gave them a very natural way to deal with the imaginary energy states by saying on the gravity side, okay, so by noting that if they impose a sharp radial cutoff on the gravity side, there are no black hole states that have imaginary energies that are allowed. Okay, so this was their proposal. Quantum pure gravity in ADS3 with a sharp radial cutoff is supposed to be dual to TT bar deformed CFTs, the ones that are dual to pure gravity, with negative mu and truncated to the real energy states. Okay, So this is, again, the proposal. And this MMV proposal is a stunningly simple holographic realization of the quantum gravity with a finite cutoff. So I remind you, previous ideas involved Wilsonian RG, but this is extremely simple, so a lot of people were interested and provided the generalizations of these ideas. And the generalizations depart from another nice observation that was made by MMV, which was that the TT bar trace relation, so TT bar, the trace of the stress tensor is not zero, but it's universally equal to TT bar. This trace relation maps to the radial constraint Einstein equation. So that's true in 3D pure gravity. And basically, the generalizations of TT bar that follow from this were generalizing the flow based on the Einstein equations. So some examples of generalizations is higher dimensional TT bar, which is engineered to reproduce higher D pure gravity with Dirichlet boundary conditions at finite radius. Applications to de Sitter cosmology, which is engineered to reproduce a flow from ADS3 to DS3. Various bulk reconstruction ideas, and so on. One important common denominator of all these proposals is that you basically lose all this, what I presented as defining properties of the TT bar deformation, such as the precise specification of the operator and UV completeness. So instead, the factorization properties of the operators are replaced by large N factorization, and the theory is no longer assumed to be UV complete. However, they get interesting results from all these generalizations, and at the end of the day, it seems that sort of what is really needed here is just having some sort of definite or tractable quantum mechanical system that's dual to gravity in a finite volume. And with only some TT bar properties, but not all of them. Okay. And as far as open questions are concerned, I think it would be nice to just going back to the original, setup with actual, 3D pure gravity and actual negative mu TT bar. I think it would be nice to, try to understand this a little bit deeper. As I said, this negative mu TT bar is kind of an inconsistent theory. So it would be nice to understand if simply removing the imaginary energy states gives you a consistent theory, and presumably you want non-perturbatively consistent, and also to understand better understand the relationship between these two bulk proposals and TT bar. So it would be welcome to have an in-depth study of pure 3D gravity at finite cutoff, and that has been started by these collaborations, and also try to cook up observables that distinguish between the two possibilities. So what's been computed so far, energy and stress tensor correlators cannot tell the difference, but maybe something like entanglement entropy could. Okay. So I now come to the final part of my talk, which concerns the so-called single trace TT bar deformation. And the motivation for it was given in the introduction. So basically, we're trying to understand these finely tuned irrelevant flows. We're hoping that these finely tuned irrelevant flows can give rise to, non-ADS holography via this sort of setup. And as you've seen, the standard TT bar deformation doesn't do the job for us because it's double trace, so it just does mixed boundary conditions. So in order to get non-ADS holography, you really need a single trace variant of TT bar. And at the field theory level, there's a simple observation made by these people. So let me say in ADS3 CFT2, usually the gauge group is given by permutations. So the observation is that if you start from a CFT that's given by a symmetric product orbifold, then you can easily construct a single trace generalization of the TT bar deformation given by a sum of copies of TT bar. That's a single sum. So it's defined that finite mu, just like the standard TT bar, is completely solvable, and it turns out to be equal to the symmetric product orbifold of TT bar deformed CFTs. Okay, so let me try to expand on this, the proposal by Giveon, Itzhaki, and Kutasov. So more precisely, what they consider is a string theory setup. They consider a stack of N5 NS5 branes and N1 F1 strings in the NS5 decoupling limit. So it's this one. And the background, they consider interpolates between ADS3 and the IR, and asymptotically flat with a linear dilaton in the UV. And it's holographically dual. In the UV, it's described by little string theory, which is a non-gravitational, non-local theory with the Hagedorn growth of states. Not much is known about it. And in the IR, the ADS3 is at least partly described by a symmetric product orbifold of some CFT with center charge 6 and 5 with respect to the number of F1 strings. I'll come to this later. So what these people noticed, so if you consider worldsheet string theory in this background, the worldsheet sigma model in the full background is an exactly marginal deformation of the WZW model that just describes the ADS3 part by a current bilinear. And they identified the holographic dual to this deformation in the proposed spacetime CFT, and it turns out to be dual to a CFT source for a 2,2 single trace operator, which they argued is the single trace TT bar. And now the point is that this deformation is exactly marginal, so it can be turned on a finite amount, and so can single trace TT bar. So they propose that the partition function of string theory on this background is captured by the partition function of symmetric product orbifold of TT bar deformed CFTs, and there's this map between the TT bar coupling and the string length. And you can have a similar construction for a single trace JT bar, which actually gives first concrete microscopic realization of the Kerr CFT correspondence. Okay. So given this proposal, you can try to perform various checks. So one check that the authors performed was to show that the spectrum of long string excitations in this theory exactly matches the single trace TT bar spectrum. So that's a nice check. Another check in the earlier paper was to show that the entropy of black holes in this background, so you can have black holes that fill up here, precisely agrees with the TT bar entropy. So it has some interpolation between Cardy behavior at low energies and Hagedorn behavior at high energies. Okay, so both of these seem to support that claim. Except that the situation is a little bit more complicated than that, for the reason that it's not exactly true that the seed theory that you start from is exactly a symmetric product orbifold. So let me try to explain that. So if this is the D1, D5 moduli space, okay, there's a point in the moduli space which is a symmetric product orbifold, the D1, D5 CFT. The calculations in this setup are done at some other point in moduli space, which is dual to this pure NS background with N5 greater than 1 and S5 branes. And the holographic dual to this background has actually been proposed to be a deformation of a symmetric product orbifold by an operator from the twist-2 sector, which destroys the symmetric product. And what's left? Well, basically, you can still argue that long strings can still be described by a symmetric product, but not the full theory. So in a certain sense, this result simply follows, is in agreement with the fact that long strings are well described by a symmetric product orbifold, but this result doesn't really follow from that, and it's a little bit more mysterious where it comes from. It might have a different physical interpretation. Okay, one can match other things, so one can look at correlation functions of operators in momentum space. So these space-time correlation functions can be computed using worldsheet techniques, and one finds some answers, and those answers do not seem to match what one gets from the symmetric product orbifold, which would predict that one should get the same answer as in double trace TT bar. Okay, for double trace TT bar, we don't really know the answer, but for JT bar, we can see that they're different. But that's not a surprise. It's explained by the fact that these operators are really from the short string sector, so they don't really need to match. Another nice thing that one can compute in this setup is the holographic entangled entropy. It's been studied using the Ryuta-Kanagi formula. And it has some nice properties. So first of all, it's logarithmically divergent so it's log of L over some cutoff, just as in standard ADS-CFT. And the effect of the non-locality of the dual theory on entanglement entropy is that there's a minimum length of the boundary interval for which the Ryuta-Kanagi surface actually doesn't exist. And this L minimum is basically this sort of little string length. And you get similar results actually for the two-interval mutual information, which diverges when the distance is L-min. Okay. Finally, something that one can do in this setup, try to study the... is it completely over? 10 minutes to go. Okay, I must have spoken really fast. Okay, so something that's interesting that you can study in this setup are the symmetries. So I have argued before that the standard TT-bar deformed CFTs have Virasoro symmetries. And in some work in progress with Sumangsu Chakraborty and my student Silvia Georgescu, we showed that these symmetries actually survive the symmetric product orbifold. So what this means is that basically this theory over here has Virasoro times Virasoro symmetry. And we wanted to see what's the situation with the theory over here. So for this, we performed an asymptotic symmetry group analysis of the dual background, this asymptotically linear dilaton background. And our results started preliminary, but we have an infinite set of symmetries whose algebra seems to be Virasoro times Virasoro. And I guess this result will be confirmed. But what's interesting about it is that, as I tried to explain before, this result does not follow from this result on the symmetries of TT-bar symmetric product orbifolds, because this point in moduli space does not correspond to a symmetric product orbifold CFT. We're really talking about the full theory. So it's interesting to think, what could explain such a result, and a possible explanation would be if, so at this point, where we have the exact symmetric product orbifold, there's a well-defined single trace TT-bar deformation. And it may be possible to actually try to sort of transport this deformation over the modular space. I have no clue how to define it, but maybe there do exist sort of irrelevant deformations that start as a 2,2 operator that lead to UV complete theories, starting at an arbitrary point in modular space. So the Giveon Kutasovic-Saki deformation would be one of them. And then maybe the Virasoro symmetries that one has here may extend to Virasoro times Virasoro symmetries over all these theories. So this is a setup that could explain why we should be seeing Virasoro symmetries at this point. Of course, a lot would need to work in order to show that, but it would be an interesting possibility if all the theories so defined could be this type of non-local 2D CFTs. So with that, I'll end. Thank you very much.
Any questions? Was that clear? Yes.
Hi, Monica. You very quickly mentioned the comment about the microscopic realization of Kerr CFT. Mm-hmm. Maybe you could briefly elaborate on that. Thank you.
Where is it? How it works? Well, so you can again start with this ADS3 is supported by purely an SNS fluxes, and have a background that at the level of the worldsheet you'd be turning on some other type of exactly marginal deformation. It's J minus K3 or something like that, and that is conjectured to correspond to single trace JT bar, the same thing. And the background, the full background that you get from this exact worldsheet description is warped ADS3 supported by an SNS. So to the extent that CurseFT is warped ADS3 duality, that's it. And actually, Wei and Song and Luis Apollo have been computing a lot of things in that duality. But everything that I said over here about whether the starting theory is symmetric product or bifold also applies to that setup, so one has to be a bit more careful.
Just to be clear, the warping that you get actually has the correct dependence on the polar angle?
No, it's a very special string theory setup. You want to get the basic QFT properties of the theory, and yeah, it's very idealized.
At one of the earlier slides, you had something about the theory that it has non-Lorentzian symmetries.
Sorry?
Non-Lorentzian symmetries.
Oh, yeah. This was JT
do you
bar.
know what it is? Is it something Galilean or something Carolian or nothing you have ever seen before? Or it's just it's not?
It's non-relative. Well, so the symmetry group, the global symmetry group, it is SL2R times U1, and the U1 is non-local. If you were to do this in higher dimensions, basically you'd be doing a KK reduction on that U1 to get a non-relativistic theory in the remaining directions. So this would be like a non-relativistic quantum mechanics, but you can do this construction in higher dimensions.
So by non-relativistic you mean like Galilean or?
So JT bar, the single trace version of JT bar is related to this basically null warped ADS, which is the lowest dimensional example of a Schrödinger spacetime. And Schrödinger spacetimes have been connected to non-relativistic, but you see the non-relativistic structure is codimension 2 in that case, and the same is true here.
Okay, thank you.
Yeah.
So you mentioned several times that this TT-bar deformed 2D CFT can be thought of as some non-local CFT. So I was wondering if you have some kind of axiomatic definition of what these non-local CFTs are. And if you do, how does the usual Cartesian gluing consistency conditions for 2D local CFT, what do they become in this context?
Yeah, so as I said, in the case of JT bar, what we can do, we can so in a standard CFT, what's important is that you have some basis of local operators which transform nicely under conformal transformation, and those correlation functions are heavily fixed by conformal symmetry. So this is why it was important to find these analogs of primary operators in JT bar, and in a sense, we can just compute exactly what their correlation functions are. I think I had a slide saying something. So just using the particular deformations, what you find is that the momentum space correlation function in this theory is just the momentum space. It's maybe simpler to look at 2- and 3-point functions, where these correlation functions that you can compute exactly because you know exactly what the primary operator in JT bar is. So you can compute that correlation function exactly, and you find the original CFT momentum space correlator at dimensions shifted to some particular momentum dependent conformal dimensions that are quadratic in the momentum. So you actually have an expression for the full correlation functions, and then you can sort of work backward if you want, and try to see what are the consistency conditions.
But are you suggesting that, for example, I can determine the genus?
Sorry, I can't hear very well.
So are you suggesting that, for example, I can determine the genus two-boundary function using their three-point function together with the cylinders just by gluing?
I didn't understand, sorry.
So I was asking, are you suggesting that I can determine higher genus Riemann surface boundary function, like genus 2 Riemann surface boundary function, starting from the three-point functions you have here and the cylinders and by gluing?
I should say that these calculations were so the calculation of the correlation functions that I'm referring to here are in a certain sense Lorentzian calculation. So you're really looking at the flow of states and the flow of the Hamiltonian, the flow of the operators. I don't know how to make sense of them in Euclidean language. So the short answer is that I do not know, but the main, so it was important over here that we could get finite results for this correlation function, but they just came from a Hilbert space interpretation of the flow, and I don't yet know how to generalize it to the standard Euclidean calculation.
Okay, thank you.
Is there an analog of the cutoff ADS tree proposal for JT bar deform theories? Because in JT bar, like the wrong sign TT bar, the energy spectrum in the UV is also complex.
Well, so the only holographic proposal that I know for JT bar is these mixed boundary conditions. So JT bar is dual to pure, you need to have at least 3D gravity coupled to a Chern-Simons gauge field to model the J and the T bar, and then you get some mixed boundary conditions, which look like, if you know what these boundary conditions are, okay, fine. How to say, as I try to explain in this talk, this whole cutoff ADS idea is the result of a sort of huge coincidence that was happening in the case of TT bar. The general case, when you have matter for generic CFT, is actually mixed boundary conditions at infinity. And it's only in very special cases that it ends up looking like cutoff ADS, if you can argue that it's consistent to throw away these imaginary energy modes. So for me, that cutoff ADS is a coincidence. The general thing is mixed boundary conditions, and JT bar, it's some different type of mixed boundary conditions.
I see. Thank you.
Hi. So here, if you remove this bulk Chern-Simons field, will you still get these CSS boundary conditions or some analog of that?
Very good. So, yeah. So these boundary conditions were obtained, as I explained, for TT bar. You start with the field theory, you do Hubbard-Stratonovich, and then you derive it. In that case, you must have the Chern-Simons field. So an important thing about these boundary conditions is that they allow for full propagating matter, whereas CSS do not, and you can relate it to the fact that in CSS the gauge field is absent, so you have to restrict the matter sector. Yeah, but it would be interesting to work out the correspondence between the two.
So any further questions? Should thank Monica again.